Hi, my name is Sam Sandoval. I'm a faculty and an extension specialist at UC Davis and also at UC A&R. And today we're going to be talking about water resources modeling and optimization model. So again, in this video, we're going to be talking about a very brief explanation of water resources modeling and also things related with optimization modeling. So again, as we mentioned, we have in California different water resources systems, or one water resources system that is actually quite complicated, where we're moving water pretty much north to south and also from the east to the west. This is kind of the surface water system that we, as we know, with the Central Valley Project, the State Water Project, all the different local projects here. In addition, so that will be a conceptual model of the different canals, aqueducts, and how we're moving water. This will be similar representation, a different representation, but now considering, in this case, groundwater, a little bit less conceptual, more descriptive of what it is. Again, in how to operate this system, we need to find tools to, in this case, manage, distribute water. Last class we were talking about simulation models, and basically simulation models, they are predictive models. They predict the response to a given design. And what does that mean? That you have a water resources system, you set as an input some of the, in this case, some of the hydrology, and you specify the water allocation system. You specify the different infrastructure and what are the different rules that this infrastructure will be operated. And at the end, you estimate an output. You may change either some of the hydrology, or you may change some of these operations, these water allocation policies, or how you operate infrastructure, and you will have a response to that alternative design. So this is more iterative, and basically the simulation model responds to what if questions. Now, optimization models, they look for an optimal design. They look for what are the opportunities that the system has so it can be operated at an optimal level. And that's basically what optimization model does. Again, just a friendly reminder, in the previous class we talked about simulation and that they respond to the what if questions. What would likely happen if I change this or that? In this case, again, just to reiterate, simulation models are, you can estimate what is the change, what will be the response given a change in a policy or in some infrastructure. The optimization models are different. So basically they are used for design and also to obtain some insights on a given system, okay? When in water resources management, when we're talking about optimizing resources, we are referring to either maximize certain a given objective or minimize certain objective. In the case of maximize, you can think that you want to maximize the net benefits, the overall benefits that you can get out of a system. Some of those can be expressed as dollar values, but some other ones cannot. So not necessarily is when we're talking about benefits, is not a dollar value. It can be, in this case, it can be production. You can also include reduction in floods or a given health in the soils. There are different types that you can think of benefits, water for the environment and so on, or minimize shortages. That will be another way. But please consider that every time that we're talking about this, it is basically about maximize or minimize. An optimization system, or when talking about optimization in water resources management, is minimize or maximize. Then the next one is that we're looking for that optimized operation, best or ideal operation. Again, we want to look for these insights. What are the places where we can operate a system ideally? What will be the capacities? Some of the things that you're going to see is that it has perfect foresight. And basically, when you're running a time series data, it is not stopping at a given step and looking what can it do to the next step given the previous information. No, an optimization model can see in the future, or if it is at a given step, it can see all the different inflows at a future time step and what happened before, and decide what will be the optimal solution given those conditions. So it has a perfect foresight. It analyzes the data as a whole, not step by step. It looks at the entire data. That's what is called perfect foresight. Again, in this, what you're going to see is that, for instance, for this system that we already know, we can think that we want to maximize the benefits for users 1, 2, and 3. So this summation of the benefits. The decision variable will be how much water can be diverted from these 3 users. That's why we're calling something like that. And then the objective is to maximize the benefits for these users, given that we know that it follows a mass balance operation. The storage has to be less than the capacity. The storage at a given time step is the storage at the previous plus inflows minus outflows, and the releases have to be equal or less than this kind of x1 plus x2 plus xt users. So it's following a mass balance, okay? Now, let me talk about some general concepts. Again, when we're talking about optimization, you want to identify key variables that you want to optimize. And you want to optimize a desirable function. So these key variables, we call them decision variables. And you want to optimize, you want to define if you want to find the minimum value or to minimize something, or that you want to maximize a certain expression, a certain objective. This objective, we call it in terms an objective function, an equation. It is the equation that defines our objective. That's why we call it objective function. It could also have been called the objective equation. It's the equation for the objective that we're doing it. The variables that are in that specific function are these decision variables that we're going to start tweaking around, okay? And this function that has certain variables, we're going to find if we want this function to minimize it or to maximize it, okay? So those are the general concepts, and the rest, it will come a little bit easier. So what are the steps for linear programming? What you're going to see is that we have 7 steps for linear programming. The first one is that, again, you need to identify this function and what are the decision variables that you want to use. And what I talked in the previous slide, do you want to maximize or minimize? The next one will be to, once you have identified your variables, if you want to minimize or maximize, then you need to write down the objective function equation. This equation to come up with this, to define what you want to minimize or maximize. Once you have written down your objective function equation, your objective function, then you're going to be defining the constraints. So writing equations that those variables, how you're going to constrain those variables, okay? Next one, you're going to define a feasible region that you can think all those conditions are true. The next one, you're going to obtain the corners, the vertices of that feasible region, because that is the location when you're going to find the maximum value or the minimum value. Once you have identified those corners, those vertices, then you're going to substitute the value of those vertices in your objective function, and you're going to find what is the value that maximize or minimize. So you select the data. So let me explain you an example here, so we can kind of bring all of this theory into some application. So think of this. Think that you're working in a farm. So as you're working in this, one of the objectives of the farms are to, or in theory of agricultural production agriculture, is to maximize the profit. Yeah, you're growing, but at the end you also want to get some profits out of it. Ideally, the largest amount. So in this specific farm that we're seeing here, it might be that this farm only has 1,800 acre-feet of water. This is their water right, so that's what they will be using on an annual basis. Also, consider this. So this specific farm has these water requirements. So you want to plant 2 different types of crop. one that we're going to be calling crop A, and another one that we're going to be calling crop B. So for instance, sunflowers, and in this case is corn. So think about this. This specific crop A, you can plant up to 400 acres. And out of these 400 acres, each out of this acre of this crop A, you're on average having a profit of $300 per acre. So that's pretty much what you're economically getting out of it. And on each acre, you're applying 3 acre-feet per water. So imagine the land or the area of an acre, and then you put on top 1 foot of water. So specifically, this crop will require a 3 acre-feet per acre. This should be something between olive trees and perhaps some pistachios, almonds. So that's kind of be one of those that use that much water. Now, for crop B, you can plant up to 600 acres. So that's how much you can actually apply on it, that you can grow or that you can produce on this area. You get out of it $500 per acre of each acre of this crop too, and it requires 2 acre-feet per acre of water. Again, this will be something in more on the side of a lettuce, some vegetables. So let's actually go back here and think about our 7 steps of linear programming. So we want to maximize the profits, okay? So the first step is to identify the objective function. What do we want? So we do want to maximize the profits. So in this case, this right here, we're identifying it. So this will be our step 1. We're identifying that we want to maximize. Now, do we have any decision variables? Yes, I've already, or they are already here mentioned. So the decision variables, so we want to maximize the profit to find what is the acreage of the 2 crops that we have or that we know how to grow in order to maximize those profits. So in this case, it will be the acreage of the crop. So in this case, we have XA and XB. So that's what we want to, those are our decision variables. Okay. Now, we have identified, so we know our objective function, and we have identified our decision variables. In step number 2 is define the objective function, pretty much write the equation. So how can we write an equation? So what will be the equation for the profits? So let's write down here profits. So how can we estimate the profits? So the profits can be estimated for crop A, by multiplying how much you get out of an acre of crop A. So in this case, it will be 300, times the number of acres that you are producing that specific crop. And in this case is this XA. Plus how much you get out of planting crop B times the acreage of crop B. So that will be writing the objective function. So in that case, we're good. We have actually done step number 2. And in reality, what we want to do is we want to maximize C, which in this case, C would be equal to the profits equal to that equation. So we're good. We know that we want to maximize those profits, and we have an equation for those profits. Finally, we want to, in step number 3, we want to define the constraints. So what are those constraints? So we have constraints related with the area. So in this case, XA, so the acreage of crop A has to be greater or equal than 0, and similarly, XA has to be less or equal than 400. We can do the same for crop B. So the acreage of crop B has to be greater or equal than 0, and it has to be, XB has to be less or equal than 600. Okay, so that's how we're including this portion in here. Now we have another constraint in here, and it is the amount of water available for the farm, which is 1,800 acre-feet. So how can we include that? So how much water is using crop A? So crop A is using 3 acre-feet per acre times the number of acres for crop A plus 2 acre-feet per acre, or the amount of water in one plot for crop B, times the number of acreage of crop B, and this has to be less or equal than 1,800. So there we go. In here we have defined our constraints, and this will be accounting for step number 3. Now, so I think we are, in this part we're good. We are actually moving good in our defining our optimization model. So that's good. Now let's think about this a little bit more without actually going brute force on the mathematics. So think about this. This crop A, so we want to identify this acreage of crop A and the acreage of crop B, given all these different considerations. So if you were a farmer, how much would you plant without actually doing all these mathematics? How much would you plant of crop A and crop B? I know that's the initial question that I put it in here. So now I want you to look at these two values. The profit that you can get out of an acre from crop A to crop B. So which one gives you the most profit per acre? A or B? B. B gives you the more profit per acre. So how much would you want, how many acres do you want to grow of crop B? Ideally 600. You want to maximize, or you want to get the most acreage that you can of crop B, because that's the one that gives you the more profit. So if that is the case, then it will be 600 acres. What will be the other limitation that you will have in order to grow 600 acres of crop B? The water. So the next limitation will be the water. Do I have enough water to grow 600 acres? So if I multiply 600 times 2, which it will be the amount of water that crop B used per acre, so in that case it will be 12 acre-feet. Okay, so yeah, 12 acre-feet is less than 1,800. So yes, I can actually go all the way up to 600 acres of crop B. What else can I do? Well, the remaining water, which that remaining water is 600 acre-feet, I'm gonna use it to grow crop A. How many acres can I grow with 600 acre-feet? Well, you divide 600 over 3, which is this guy here, and it will be 200 acres. So without actually going through all the math, what I'm thinking is that the solution will be to try to grow as much as crop B, and then whatever resources I have remaining, I will use them to grow crop A. Okay, so for now, I think we have a good hint that perhaps this might be the solution for the problem, okay? Well, let's actually go to the next step. So going back, so we have identify our objective function, define the objective function, so we have write the equation. We have also defined the constraints, so we have this set of constraints in number 3. And now we need to define the feasible region. So what do I mean by feasible region? So we have these different constraints. And how can I think of those constraints in terms of this kind of XY plane? So XA, so the x-axis is XA, the number of acres. For crop A, XB is the y-axis, and it will be the number of acres for crop B. Okay, so in theory, not in theory, the objective function here, these are telling us that the crop A we have to use from 0 to 400. So how can we actually use this information to define this feasible region? So in this case, this guy here, XA, has to be greater than 0. So this value has to be on this side, okay? So an arrow towards this direction. Also, it has to be less than 400. So XA has to be less or equal than 400. Okay, now what about on XB? Well, on XB, it has to be the same. XB has to be greater than 0, and XB also has to be less than 600. Okay, so we have now these two. What about that other equation that we have in there, which is 3XA plus 2XB, the water constraint? So in that case, what we're going to do is that's what you're seeing here, this is a line. We now need to make sure, well, we have to make sure that we draw the line correctly. So how can we do that? Well, there are different ways. One of the ways that I find easiest is to identify when this line crosses the x-axis, in this case XA, and when that line crosses also the y-axis, XB. So how can I do that? So in this case, I can do if XA is equal to 0. So if XA is in this location here in 0, where will it cross the y-axis? So in this case will be, so let me actually write here the equation. 3XA plus 2XB. In this case, I'm going to write it as a question, not as an inequality. Okay. So in this case, it will be 1800. Okay. So if XA is equal to 0, then we're going to have that 2XB equal to 1800. XB will be equal to 1800 over 2 equal to 900. So this, the x-axis is crossed at 0, 900. Okay? Now to develop a line or to create a line, I need 2 points. So let me actually go and look for the other point. And it will be the same when the line crossed, in this case now the x-axis. So if XB is equal to 0, then we're going to have that 3XA equal to 1800. XA will be equal to 1800 over 3 equal to 600. So in this case, 600 will be where it crosses in here. Okay? So we have 2 points. Now we can actually draw a line. And that will be the line of that specific constraint. So there we go. That will be our line. And this line is related to this 3xa plus 2xb less or equal than 1800 constraint, which we know that it is this. So where our so what is the feasible region? And in this case, this line has to go this direction. So as you can see here, so this line has to move here, this here, this toward this direction. So this is when things are feasible. So what this means, or what this is telling us, is that this region that we're seeing here is the region that actually will be feasible for, or that the solutions that we have for our constraints, where they are actually, where they occur, when they happen. So that's basically what this is telling us. The region that I'm just highlighting here, that specific area, that will be the region that we know is the feasible region for, specifically for this set of constraints and objective functions. Okay, so that's pretty much what we have in here. Okay, so this will be number 4, so we're good. We have defined our feasible region. Next step. So this is pretty much what we did, but now done it a little bit more clearly without my poor handwriting. Now let's go to the next one. So the next step, which is step number 5, it will be to obtain the vertices. So at this point, what we want to know here is obtaining the specific values of the corners that this polygon is doing. So what are those? So in this case, it will be this here. Oh, let me just actually change it to a pen. Okay. So we want to find what are the specific corners in here. So this corner, this is what I was talking, or what I was referring about the vertices. Okay. So this one, I'm gonna call it A. This one I'm gonna call it B. This one I'm gonna call it C, D, and in this case it's gonna be E. Okay. So let me actually here draw a line and try to get something that it will be, well, let's think about this. So we want to get the coordinates for these guys here. So in this case, one is going to be the x values, so xa, the y values, xb, for A, B, C, D, and E. Okay, now this doesn't look like an A, but it's trying to be an A. Okay, so in this case, what are the coordinates of A? Here, 0, 0. What are the coordinates? So this is this guy here. What about this other guy here? So this will be 0, 600. What about C? So C, we know that on the y-axis is 600. And we kind of have an idea that it might be around 200, but we are not sure. Okay? The same with D. D, we know that on the x-axis is 400, but on the y-axis here, we're unsure. So in this part, we are unsure here, and that will be in C, and in D, we're unsure in that other side. For E, which is the last one, we know that that one is 400, 0. So we're missing here 2 different values. So how can we estimate the value for C? Well, basically I can, in this equation, in the 3xa plus 2xb, I can actually find what will be the value of that equation when y or xb is equal to 600. So again, in this equation, 3xa plus 2xb equal to 1800, So when, in this case, XB is equal to 600, then in this case it will be 3XA plus 2 times 600 equal to 1800. XA will be equal to 1800 minus 1200 over 3. 600 over 3 equal to 200. And again, we kind of have a hint that this was 200, so that's what I'm putting in here. And the next one will be to do the same, but now when XA is equal to 200. So for the same equation, it's going to write here something here. So for the same equation, when XA is equal to 400, in this case, what we have in here is 3 times 400 plus 2XB is equal to 1800. And XB will be equal to, please excuse my handwriting, it's just a little bit difficult to write it in the screen. Oh, see, I knew it. So this will be it. Oh man, sorry. And this will be divided over 2. So in this case, we're going to have the same 600 divided over 2. It will be 300, which sounds about right. So we have now the coordinates, the values of these corners. Later, as I'm going to show you, the maximum value, the value that maximizes the objective function is located in those corners. Okay, so we're good. We have gone through step 5, which is basically this. Oh, look, here I have actually where to write all these things. Hey, well, then the next one. So I have to substitute these values in the objective function equation. Just a friendly reminder that in this case, this is point A, B, C, D, and E. Okay, so in this case, when you substitute this equation, it will be 300 times 0, so 0 plus 0 equals 0. Okay, for the next one, it will be 300 times 0, it will be 0. 500 times 600 is 300,000, so in this case is 300,000. Remember that this is benefits, and this, the units of this is dollars. So we're multiplying the profit, the dollars per acre, times the acres, so that's what it will be in dollars. Okay, the next one, which is, so we analyze this guy here, point B. Now let's go into point C. And in point C, we're going to have 300 times 200, it will be 16,000 plus 300,000, it will be 360,000. Okay. The next one will be point D, which is 120,000 plus 150,000. It will be 270,000. And finally, the last one, it will be 120,000 plus 0 equal 120,000. So that's step number 6. We have substituted the values in here in this objective function. So what is the value that maximizes the profit? So in this case, it's going to be this point right here, point C. So this is the one that is maximizing the profit out of it. So what will be the combination? XA will be equal to 200 and XB will be equal to 600. And that was something that we were discussed before. Remember when I was telling you, like, let's think a little bit this more calmly. The reality is that the model tried to grow the more of the one that is the most profitable, and then see with the remaining resources what can it do to get the most out of it. So this will be how you will solve it. Now let me actually talk to you about some key concepts. So far in the previous one, we were just discussing about the constraints and then finding this feasible region here to estimate what was the location along this area where we have the most benefits, the most value of this specific equation. So far we haven't actually printed out or worked with this objective function equation. Let's see how that line look like. Okay, so I'm gonna do exactly the same as I did with the previous one. Remember that this one, the value is 360,000. So what I'm going to do this is that I'm gonna set this one as 360,000, that we know that's this point in here. And basically what I'm going to do is, so we know what are those coordinates, okay? But I don't know what is the slope, I know that equation is passing through there. I want to know how that line actually look like, okay? So in this case, what I'm going to do is to say, like, well, what if XA is equal to 0? So again, in this equation, if XA is equal to 0, then XB will be equal 360,000 divided by 500. And this one will be 720. Okay, so when XA is equal to 0, here it crosses at 720. Okay, now let's do the opposite. If XB is equal to 0, then it will be XA will be equal to 360,000 divided by 300 is 1200. Okay, so in this case it will it will cross in here. Okay, so this, if I have the right pulse, which I didn't have it, but this would look something like this. Okay, this is what it would look like, that specific line. And sorry that it didn't go that right, but so in this case, that's the line that we want to analyze. Sorry. So let me talk about a little bit of some key concepts that we need to discuss. So in this case, what we have in here is that we have discussed a lot about the feasible region and substituting those values in here, but we actually haven't looked at the objective function, the line that this is creating. So I'm going to use this value here, our maximum value for the objective function, and I'm going to use that one, put it in here. And I'm going to use that value to actually estimate what will be the line if we draw it in here. So I'm going to do exactly what I did with the previous one to estimate where that line, to draw a line from here, which is basically is that I'm going to find where it crosses the x and the y axis. Okay, so how do I do that? Well, I know where it crosses the x-axis when xb is equal to 0. So in this case, if xb is equal to 0, then xa will be equal to 360,000 divided by 300, and that will be 1200. So that will be right here. Okay. Now the opposite, if xa is equal to 0 when it crosses the y-axis, xb will be equal to 360,000 over 500. And this will be 720. Okay, so that will be somewhere here. Okay, so we know that this line passes through here because that's what we did in here, but it also does these three points. So I guess that line will do something like that. Okay, didn't go that straight, but that was a good attempt. Okay, why do I want it to? Definitely this is easier on the whiteboard. So that's the line. Why do I want it to draw it? So what if, so this line, as you can see, we evaluated somewhere in here, and we evaluated also somewhere in this corner. So we evaluated in this corner here, and then also in this corner here, and then also in this corner here. So basically we were evaluating this line, and as we were trying to maximize, we were moving it towards that direction. The last point that it actually touched the feasible region, it was here. So that's why, that's the first thing. That's to let you know that the maximum solutions always happen at those corners. So that's one key concept. That's why we are evaluating always in these corners. Now the other thing that I wanted to mention is the slope of the objective function. So far we have this equation here, like what we have it in here, this 300 xa plus 500 xp equal to 360,000. But we don't have this equation actually in the form that is more common for plotting things. And that form is y equal to a plus mx. So the intercept and this is the slope. So we have the intercept, and excuse my handwriting, it's a little bit difficult to write here. So we have y equal a plus mx. I know some of you were having nightmares of seeing all of this coming back from high school all the way to college. I'm sorry. I think at that point when you were learning some of this algebra, it was just a little bit abstract. This is a way that you actually can use it. And so how can we convert this equation into something like this? Well, we know as a matter of fact that xb, this guy here, is our y's. This xa is our x. So basically we just need to put it in that specific format. So in this case, xb will be equal to 360,000 minus 300 xa, and all of this divided by 500. In this case, xb, 360 divided by 500, that's something that we have already calculated. Is this 720? And we knew that it was 720 because this point here, this 720, This is the intercept. Is where actually the line crosses, in this case, the y-axis. And then if we divide 300 over 500, it will be 0.6 XA. So this one, it has a pretty, it is very similar as, sorry, this should be A. It looks more like a D, but it is not, it is an A. This looks more similar of the equation that you used to look in algebra, okay? Why I'm making all the fuss about, I mean, if you already haven't had enough torture, why do I making all the fuss to actually put it in this form? Let me explain you why. This slope here is minus 0.6. Basically what it's telling us is that it is this case. It is a negative slope, okay? So that's why it has that specific direction. Now, again, why I'm making all the fuss? Basically what this is telling us is that, sorry, for 1 unit that you do on the run, it will be 0.6 units that you do on the rise. So remember that is rise over run. So 0.6 over 1, that will be the rise, this specific slope, okay? M, it will be 0.6 over 1. So remember the rise over the run. In this case is negative, so that's how we know that it's going this direction. So a slope of 1 to 1 is a 45 slope. So that 1 to 1 slope, if you look at this, it will be something like right in this one here. So when it's going exactly diagonally, that will be a slope of 1 to 1, okay? This one, it's a little bit shorter. This is something like this. Actually, it will be a little bit higher, okay? Why? Because we know that it is 0.6 over 1. Okay, so it will be a little bit above here, and this will be the slope. What will happen if the opposite? So this will be when m. So this will be when m is equal to 1, or when the absolute value of m is equal to 1, because we know that it was negative, so it's going this direction. This will be when the absolute value of m, sorry, it's difficult to write in here. Up. So this will be the case when m, the absolute value, is less than 1. What will happen with the other case? So when m is greater than 1. In this case, when m is greater than 1, basically what it will happen is that for 1 unit on the run, it will be a little bit more on the rise. So this will be steeper. What this means is that this one is steeper, this one is less steep, and this is actually at 45 degrees. Now again, why this is important? So think that currently we have this red, this one here, okay? So this is the one that we evaluated in here. What about if it is steeper? If this is steeper, then what it will happen is that as we're doing this, the last point that it will touch, it will actually be this corner, not this corner here. So that will be also, if when you are thinking about the sensitivity of having these XA values, or these values, these $300 per acre of XA and $500, that will be the case when this happens. So in theory, that should be the case. So if we try it quickly, so what I've done here is that rather than being 300 times XA plus 500 times XB, I'm actually switching this. And by switching this, I'm actually putting the slope, the absolute value greater than 1. So that's what I'm doing here. In this case, we can actually we can test these values in here, and in this case will be 500 times 200, it will be 100,000 plus this will be 180,000, so it will be 280. Okay. And the following one, 200,000 plus 90,000, it will be 290K. So in this case, this will be, if we modify these values here, we still, these points are still valid. So this is still point C, and this is still point D, which this will be the coordinates of point C, and this will be the coordinates of point D. But in this case, the maximum value will be there. And what we're suspecting, if we do this math, sorry, it will be 500XA plus 300XB. In this case, I'm going to use the maximum value, 290. Okay. So again, if I want to put this in the form of y equals a plus mx, in this case will be xb 290 minus 500xa, all of it divided by 300. So this xb will be equal to 1000 minus 1.67 xa. And this is, remember, so now this will be a plus mx, this is y. So here m, the absolute value of m is greater than 1. So what we were thinking is that this is a little bit steeper than the previous one, which it was 0.6, which it was something like this. And because it is now steeper, the last point that is touching this part is in here. Actually, we could know how to draw this equation here, and we know that because the intercept of x is 1800. So we have 2 points where we know that we have that line. So that will be it. And as we know, that will be the last point where it touches. Okay. So now all of that you have actually, or we could actually have done it a little bit easier in our exercise. So here we have the previous conditions, which they were these guys here. And as you're going to see on the tutorial, you will figure out how to set up your model. But basically, it's telling you the same. So this is, let's start that we do not know how many. This point here, it will be the location of this x0 or this xa and xb. This is 300 times xa plus 500 xb. This is our objective function. We have generated this constraint that xa has to be less than 400. Similarly, greater than 0, xb less than 600, greater than 0, and these 3 xa plus 2 xb is 1800, okay? And these are the profit per acre. This is actually also the duty, how much water is used per acre feet, okay, in an acre. So what you're going to do is you're going to set up this model. When we hit solve here, take a look at how this point is changing. So it will try to go to the different corners. It will happen way too fast. But basically it will go to the corner that we know it is working here. Okay? Now something that you know is that this red line, this black line is actually the line of the objective function. Okay? So again, we could have gone here and actually evaluate the first 0, 0. So in this case it will be 0, 0, and our objective function is 0. For the next one, 0 and 600, 0 and 600, sorry. and it will give us 300. And as you can see here, the line is moving towards this point, and this is our objective function. Because we know that the slope is not as steep, is slider, then this will be the last point. So the following point, it will be this 200 times 600. This is the last point where it will touch it, and it will be 360,000 acres, dollars, sorry. Now, we could have done basically what I did, which is basically switching this. So that's the last portion when I estimated the slope. And as you can see here, the slope changed completely, okay? And now if we again solve the model, basically it will go here again. And we knew that one, that will be 290, the maximum solution, and that will be for this portion here. This is this value that we were discussing here. What I wanted to show you is how to do it, or what this software is doing for you now. The last part that I do want to discuss here is these constraints. And what are the constraints? That they are binding, that we have binding constraints and non-binding constraints. What does that mean? Okay, what that means is that we know that this point here is the point where we have our objective function. That's when we are maximizing the values, and we know that this has a line something like this. It will be a little bit more steeper, but give it or take something like that. Okay. The constraints that are impeding that this objective function move more upwards are two. So one is this, and the other one is here. Okay, so these are our two binding constraints. So the constraints that are binding the objective function, that are impeding that you can get more. Those are the two ones. So these and these are the ones that are binding the solution. What are the non-binding? This. So why is this important? Because of the following. There is something called the Lagrangian multipliers or the shadow price. What does that mean? So this is for one unit that I relax this binding, how much more can I get? So what if, so we know that with this one, the value here is 360,000. Okay. What if rather than this being 600, this is 601? How much more can I get if I relax one unit of this specific binding constraint, which it will be the XP. So let's actually go here, and rather than having 600, we're going to have in our objective function 601. Okay. I think we have, this should be 300 and this should be 500. So we went to our original solution and then we solve it. Okay. The value that we have now is 360,300. This is 360,000. Up, sorry, 300. Okay. So I gain the Lagrangian multiplier for this constraint. Sorry, let me actually, give me a second here. So the Lagrangian multiplier for this is $300. So every time that I relax this one unit, I will gain 300 units more. And that is basically this. So if we went through all of this, now the new points will be 199 because we're moving a tiny bit towards the left, and then one unit up, so it will be 199.33 and 601 acres, which that's why we are relaxing that one. Now let's go back here and then actually do estimate the Lagrangian multiplier for the other binding constraint, which is the one on the water. So let's have this at 1,801, and then we solve it. And then in this case is 360, 100. In this case, if we relax it, if we relax this to 101, sorry, our value here will be 360,100. So in this case, the Lagrangian multiplier for this guy here is, is 100. Okay. What does that mean? That you will get $100 more if you relax that one. In this case, the values will be here 200.33, and the other one will be the same 600. Yeah, because we only relax that one. Now, also we call that one the shadow prices. So the shadow prices of the first one will be 300, and the shadow price of the second one will be 100. If you look at this, when we were solving this, those shadow prices actually appear in here. So we have that the shadow prices for this is 300 and 100. It already knows what is the, so automatically the optimization model is calculating the shadow prices for you and are telling you that this constraint, it's worth 600. So it's telling you O16 and Q16. So this O16 less or equal than Q16. This is $300, and this one, it is $100. Why is this important? Well, it is important because think about this. What if you have the decision to get a little bit more, what would you like to invest? Would you like to invest in getting more water, or would you like to invest in expanding the frontier of acreages for crop B? In this case, for crop B, which it will be this shadow price here, you can get actually $600. Excuse me, $300. So that will be for, this is for this, which in this case is expanding the frontier or the acreage of crop B. The other one will be that you can get only $100 more if you want to expand if you want to get an extra amount of an extra volume of an extra acre feet of water. So this will be for increase the water. So I think if you're looking at these values, basically you would prefer, or you will gain more if you actually expand the frontier of the acreage of crop B than getting more water. And we have seen this. Agriculture in reality, it gets more if it expands the agricultural frontier than increasing water. And I mean, that's what you're seeing, all the Central Valley and all those different hills that have a lot of farm agriculture on it. They know that if they expand their water frontier, their acreage, they will get more rather than bringing more water and applying it on a land. So thanks for being here. Thank you. Have a good one. Bye-bye.